Hello Year 12s and welcome back to the series on circular functions. This is the fourth video where we will be looking at the Pythagorean identity and some additional symmetry properties. We are almost ready to start sketching graphs and solve trigonometric equations, and some of the properties in this video will seem new, so please pay close attention towards the end of the video. Alright, so let's start with the Pythagorean identity. Recall that we are working with the unit circle, which is a circle with radius 1. And I define some points with x-coordinate cos theta and y-coordinate sine theta, where theta is measured counterclockwise from the positive direction of the x-axis. So in the last video, I actually labeled this point x, y, but we could also label it as cos theta, sine theta. So this is a right-angled triangle. The base is x and the height is y. And using Pythagoras' theorem, we can say x squared plus y squared equals 1. However, since we defined x equals cos theta and y equals sine theta, we can say cos theta all squared plus sine theta all squared equals 1. And the most common way of writing this is to say cos squared theta plus sine squared theta equals 1. This is the standard form that the Pythagorean identity is written in. And you need to understand that cos squared theta means the cosine of theta squared. But here's a word of warning. Cos minus 1 does not mean 1 over cosine theta. It means the inverse cosine, which we will define in a future video. Alright, so this is the Pythagorean identity, and it's really just an application of Pythagoras' theorem to the cosine and sine of an angle theta, and this is derived from the unit circle. And one thing I should say is that this holds for all values of theta. So you can pick any angle theta, including 0 and pi on 2, pi, 3 pi on 2, etc. Because cosine and sine will either be 0 or 1 at those instances, or negative 1. So with that in mind, let's do a couple of examples where we apply this formula. So in case you've forgotten, this is the Pythagorean identity. And if we know one trig ratio, we can easily use that to find the other trig ratio. So example 1, I've given you sine theta, and I asked you to find cos theta. So we'll start by writing the Pythagorean identity. Cos squared plus sine squared of theta is 1, but we know that sine theta is 1. So we do the math. 0.6 squared is 0.36. Think of 6 times 6 is 36. And then we get cos squared theta is 0.64, taking away 0.36 from both sides. And if I take the square root, I get plus or minus 0.8. And since cosine is negative in the second quadrant, our final answer is cos theta is negative 0.8. And there you go. Now, Another way to solve this problem would be to draw a right-angled triangle with side lengths. So this is 3/5, right? So if this is theta, I could call this side 3 and I could call this side 5. And using Pythagoras' theorem, I will get 4 for the adjacent side. And cosine of theta is 4 and 5, or 0.8. Same thing, but we just have to adjust for the sign at the end because we know that the angle is in the second quadrant. So I'm happy for you to do it this way as well. You are still applying Pythagoras' theorem in that method. This is sort of a more systematic way of doing it, and this is sort of what I would expect from a Year 12 student. Okay, one more example. So here we have been told that cos theta is 1/3, and I've deliberately asked a slightly different question. I've asked you to find tan theta. You'll notice that the Pythagorean identity gives me a relationship between cos squared and sine squared. There's no tan theta there. But if you recall that tan theta is sine theta on cos theta, this will actually get us the answer that we want. So if we find sine theta, then we can easily calculate tan theta. So here we go. Cos squared plus sine squared of theta gives me 1. So 1/3 all squared plus sine squared theta equals 1. Now 1/3 squared is just 1 on 9. And therefore sine squared theta is 8 on 9. And if I take the square root of both sides, I get plus or minus 2√2 divided by 3. Now, as I'm looking at that fraction, I'm thinking, is that going to be smaller than 1? And the answer is yes, because √2 is 1.414. And if I multiply 2 by 1.4, I get 2.8. And 2.3 divided by 3 is slightly less than 1. So this is okay. Now, we have a situation where our angle is in the fourth quadrant. And so, since sine theta is I'll actually just say, I think a better way to write this is just say theta is in the fourth quadrant. Therefore, sine theta is negative, which means sine theta is negative 2√2 on 3, and that means tan theta is negative 2√2 on 3 divided by 1 on 3, and that gives me negative 2√2. All right, I'll change the top text as well. So I'll say theta is in the second quadrant. So cos theta is negative. Okay, but this all came from using the Pythagorean identity. In part 1, we didn't need to find tan theta, so we could stop at cos theta. But in part 2, in the second question, I needed to find sine theta in order to calculate tan theta, because we use this formula here. Now, very quickly, if you wanted to use a really quick shortcut with the right angle triangle, again, we could say if I draw a triangle like this, cosine of theta will be 1 on 3. And then using Pythagoras' theorem, you would take the square root of 8. And the square root of 8 is 2√2. And from that, you can deduce that tan theta is 2√2 divided by 1, which gives you 2√2. And then you adjust for the angle at the end. I recommend for the purposes of this course that you write your algebra this way, and if and only if you are running out of time, you draw the right angled triangle. Alright, so that's Pythagorean identity. I want to finish this video with something a bit more difficult, and that's some further symmetry properties. Now, these are different from the last video. Last time we looked at the base angle theta in the first quadrant, and then the other angles pi minus theta in the second quadrant, pi plus theta in the third quadrant, and 2 pi minus theta in the fourth quadrant. In this video, we're going to look at something different. We're going to look at what happens if we interchange the x and the y values and then copy that angle into the other quadrants. So let's think for a moment what happens. If I swap x and y, it's almost like taking the inverse. Which means now the angle is going to be here. Now, the angle that's made counterclockwise from the positive direction of the x-axis, it's now pi onto minus theta. Because this angle plus this angle need to add up to the right angle pi onto. So this angle in red is pi onto minus theta. And so if we define if we say that x equals cos theta and y equals sine theta as a starting point, then in this diagram what we are saying is cos pi onto minus theta is the x value of this coordinate here, which is now y with reference to the original y value for theta. So that means cosine of pi onto minus theta is sine theta, and conversely, sine of pi onto minus theta is cos theta, because the sine of this angle here is x. Now, this looks a bit abstract, so I want to make this concrete with a very simple example. Imagine I gave you a right-angled triangle with angles 20 degrees and 70 degrees. And I called these shorter side lengths A, B, and C. In this triangle, cosine of 20 degrees would be equal to A over C, and sine of 20 degrees would be B over C. Conversely, if I took the cosine of 70 degrees, I'd get B over C, and sine of 70 degrees is A over C. Notice that the complementary angles, 20 and 70, give me the same trig ratio if I interchange cosine and sine. And that's all what this result is saying. Okay, it's nothing new. So if my angles add up to 90, if I take cosine of one angle, it's the same as sine of the other angle. So you've actually seen this before. If you've done right-angled trigonometry, I've just written it differently, and I've written it using radians, which is where it might seem new. Okay, let's keep going. So before we had y comma x for pi onto minus theta, we can reflect about the x-axis to give negative y x. So again, here x was cos theta and y was sine theta. And imagine a situation where we create a right-angled triangle like so. With the same angle theta, now making an angle which is now pi on 2 plus theta. Because we've gone the full right angle and we've gone counterclockwise an additional theta radians. So if you're happy with that, we can now write down values for cosine and sine of pi on 2 plus theta. According to this diagram, the cosine of pi on 2 plus theta is the x value, which is negative y. So it's negative sine theta. Now let's think for a moment. If I take the cosine of an angle in the second quadrant, I expect it to be negative. And there's a negative sign coming out there. Similarly, sine of pi on 2 plus theta, that's the y coordinate, which is x for this point. And x is cos theta. Now again, if I take the sine of an angle in the second quadrant, I expect it to be positive. And notice, it's coming out as positive. Okay, we'll do this 2 more times for the third and fourth quadrant. So now, again, imagine a situation where we have x comma y defining x equals cos theta and y equals sine theta. I then take the inverse to get y comma x, reflect about the y-axis to get negative y, x, and reflect about the x-axis to get the point negative y, negative x, and this is theta here. This time, the angle is this, and it's 3 pi on 2 minus theta. So, according to our diagram, the cosine of 3 pi on 2 minus theta is the x-coordinate of this point, which in this case is negative y or negative sine theta. Similarly, sine of 3 pi on 2 minus theta is the y-coordinate of that point, which is negative x or negative cos theta. Now let's check. Do we expect cosine and sine to be negative in the third quadrant? Yes, because in the third quadrant, only tan is positive. The rest are negative. And finally, we have taken the inverse, y comma x, and this time I can just do a reflection about the x-axis like so. So this is my new angle theta down here. And with the reflection about the x-axis, I transform to y comma negative x. And so if I define x equals cos theta and y equals sine theta, I can now consider this angle, which is 3 pi on 2 plus another theta radians, which means cosine of 3 pi on 2 plus theta gives me the x value, which is sine theta. Notice that it's coming out positive because I expect cosine to be positive in the fourth quadrant. And similarly, sine of 3 pi on 2 plus theta is the y value of this coordinate here. And that is negative x or negative cos theta. Sine is negative in the fourth quadrant, and this is coming out as we expect. Okay. I suggest that if you have trouble remembering this, like anything in this topic, draw a diagram and see if you can derive the results, just like the way that I did with the exact values for pi on 3, pi on 4, and pi on 6. At some point in life, the subject matter that you are studying in maths, physics, engineering, or any area of study eventually becomes so complex, so complicated, that you can't remember all of it. And so I'm very understanding if you can't remember these formulas off by heart. What I want you to be able to do is draw the diagram and figure it out yourself if you've forgotten. And that way you can reconstruct the results if you need it. All right, let's do a couple of examples. So I've got 2 more examples and then we're finished. So in this first example, I've told you that sine of theta is 1/5. Therefore, find sine of theta plus pi on 2. And I'm going to do this question as though I can't remember what the formulas are. So, okay, so sine is adjacent over hypotenuse, so this is quite a large angle. Probably need to draw this larger, excuse me. Okay. So this is theta, and what I want is pi on 2 plus theta. So if I call this point x comma y, the point changes to, sorry, I've drawn this triangle wrong. 1 second. That's better. This is y comma x. And this angle here is pi on 2 minus theta. And then what I want to do is add pi on 2. Yep, so this angle here is theta. And if I do this in a different color, now I've got pi on 2 plus theta. This is messier than I was expecting, and the point maps to negative y comma x. And so if I define x equals sine theta and y equals cos theta, then sine, I should say cosine of pi on 2 plus theta is negative y, or negative sine theta, and sine of pi on 2 plus theta is cos theta. Now notice that these are the same. Theta plus pi on 2 and pi on 2 plus theta. So that's okay. It's okay that I swapped the order around because it doesn't matter if I'm adding the numbers together. Now, according to this diagram, we have shown that sine of theta plus pi on 2 is sine of theta. And sine of theta is 1/5. Sorry. No, my mistake. Cos theta. And so now I need to use the Pythagorean identity, because I don't know what cos theta is, But I do know that cos squared theta plus sine squared theta is 1. And since theta is in the first quadrant, I automatically know that sine of a first quadrant angle plus pi on 2 will generate an angle which is in the second quadrant. So I can actually take the positive square root of 1 minus sine squared theta. So here, I'm taking the positive square root. Since I already know sine of theta plus pi on 2 is positive. And we know that sine theta is 1/5, so we can just say root 1 minus 1 on 5 all squared. So this is going to be root 24 on 5, which is 2 root 6 on 5. Okay, and there's our answer. Okay, last example. I've deliberately made it a mess. So here, I've given you an angle in the third quadrant. And what I'm asking you to do is find tan of a third quadrant angle taken away from 3 pi on 2. Which means this angle is in the first quadrant. So if you're having trouble seeing this, I'll write it out for you. So if I know that pi is less than theta is less than 3 pi on 2, then negative theta is greater than negative pi and is greater than negative 3 pi on 2. So another way of saying this is negative 3 pi on 2 is less than negative theta is less than negative pi. And if I add 3 pi on 2 to everything, I get 3 pi on 2 plus 3 pi on 2. It's less than 3 pi on 2 minus theta. It's less than 3 pi on 2 minus pi. And that cancels to 0. It's less than 3 pi on 2 minus theta. It's less than pi on 2. Complicated, but that's just how you would show it if you weren't convinced of this argument that I did at the start qualitatively. Remember that the inequality signs change if you multiply by a negative number. Okay, so with that out of the way, I'm going to, maybe I'll keep that. I'll keep that just in case you want to look at it in the future. Now we need to figure out what's happening. So here we go. Here's our circle. Here's our angle, theta. Well, really, I should draw it here, shouldn't I? Well, this is tricky because if I draw this as theta, the angle theta is actually this. So maybe I won't label the angle theta. Maybe what I'll do is I'll label the angle something else. Maybe I'll just call it alpha. Okay? Now, alpha in this case is some angle in the third quadrant plus some angle, which I'm going to call theta. Actually, no, I'm not going to do it this way. I'm not going to call it theta, I'm just going to call it alpha, and I'm going to define it in the first quadrant. You'll see why this is going to make it easier. Alright, so here's alpha. Just realized I may have done something wrong on this diagram. No, I think that's okay. I think that's alright. Okay, so here's x comma y. I'm going to define x equals cosine alpha and y equals sine of alpha. Put them in brackets for consistency. Now this angle here, I'm going to call pi on 2 minus alpha with coordinates y comma x. And if I go to the third quadrant, I'll have, well, first of all, negative y x and negative y negative x. And now what I'm going to do is add pi to both sides, add pi to this angle. So now this new angle here, which I'll do in a different color, is 3 pi on 2 minus alpha. So according to this diagram, the cosine of 3 pi on 2 minus alpha, this is going to be the x value, which is negative y. So that's negative sine alpha. And tan of 3 pi on 2 minus alpha, sorry, sine of 3 pi on 2 minus alpha gives me the y value, which is negative x, or negative cosine alpha. Okay, so I'm going to copy the question again, and these two formulas, and create a new page. Alright, so here we go. Now we can solve this question. So we've derived these formulas, and now the question is, can we find tan of 3 pi on 2 minus theta? Well, remember, these equations hold for all angles alpha, so it also holds for theta. So that means tan of 3 pi on 2 minus theta is equal to sine of 3 pi on 2 minus theta on cosine 3 pi on 2 minus theta. So here I've just used the definition that tan equals sine over cosine for whatever angle I choose. And then I can simplify this to negative cosine divided by negative sine. So now all I've got to do is find sine theta. But we know how to find sine theta. We just need to use the Pythagorean identity. So we know that cosine squared plus sine squared of theta equals 1. And because theta is in the third quadrant, I'm expecting that sine theta will be negative since theta is in the third quadrant. Which means sine theta is going to be the negative square root of 1 minus cosine squared theta the negative square root of 1 minus 3/4 all squared. And if you do this calculation, you'll get negative root 7 on 4. So we know cosine is negative 3 on 4. We know sine is negative root 7 on 4. So tan of 3 pi on 2 minus theta is cosine divided by sine. And that gives me 3 root 7 on 7, rationalizing the denominator and cancelling the negative signs. So, quite a lot of steps. I would say this last part where we did the symmetry properties, this is truly Year 12 content. This is the first bit of Year 12 content that you're seeing possibly for the first time in maths methods for circular functions. When we come back, we'll start sketching graphs and solving trigonometric equations. If it's any comforts, this is pretty advanced content, what we've just done with these symmetry properties. But it has come up on exams, so we do expect that you know this, and particularly these two formulas. Not so much the other ones, but if you know these two, in theory, you can derive the other formulas as well, which means it's pretty fair game to test you on these as well. So, if you have questions about this video, please feel free to get in touch, and I will see you next time. Thanks, everyone.